bit in the beginning with some pulmonary circulation, but we're going to spend the bulk of the time talking about our hemoglobin. Okay, so we're going to talk about oxygen dissociation curves, our CO2 dissociation curves, how oxygen and CO2 are carried in the body. So lots of good stuff that hopefully you will have had at least some familiarity with. But if you don't, you're going to get more than you care to know today. All right, so starting off in the beginning, we have two different supplies of blood. We have the one that we've been talking about so far, which is your pulmonary artery and your pulmonary vein that are going to send the information that is going to allow for deoxygenated blood to come from the right ventricle to the lungs for oxygenation. So that's getting ready to send oxygenated blood back to the body. You also have a bronchial artery that, I'll raise it up a little bit so you can read above it, that is sending oxygenated blood from the left ventricle to the conducting airways of the lungs because they're cells too and they still need oxygen and nutrients. So they need to get oxygenated blood in order to survive and perform their functions. So you have two different supplies. Now, both of them are going to, for the most part, return to the left side of the heart, the left atrium, via the pulmonary vein. So you do actually end up with this little shunt here that's shown in that kind of purpley color there. That is the blood that is coming from the bronchial artery, feeding oxygenated blood to your lung tissue, and it will have some partially deoxygenated blood that will mix in with the pulmonary vein. The total amount of blood that is coming back in venous return from your bronchial circulation is really at most 1%. So it's a pretty insignificant amount compared to the rest of the blood that's returning to the heart, but it does contribute a little bit of deoxygenated blood to the left atrium. So you are slightly less than completely saturated when entering into the left side of the heart. Okay? That kind of accounts for very subtle, small differences between the cardiac output on the left side versus the right side. It's pretty much insignificant, so we sort of just say uniformly that you get equal cardiac output on the left and the right. But the truth is that you have a little bit of less saturation of oxygenated blood returning back to the left side of the heart than you would expect if you weren't mixing in any of this little deoxygenated blood. Okay, so two different blood supplies. One that is there to add oxygen to the blood that's going to go to your systemic tissues, and the other that's going to provide the oxygen and nutrients to the cells themselves so that they can continue to function properly. All right, so in terms of our pulmonary blood flow, one part I want to point out is specifically looking at, on the top here, we have our aortic pressure on the top. That's our pressure on the y-axis and its time on the x-axis. You'll notice the aortic pressure, as we talked about in cardiovascular, is a lot higher than you would find on the right side of the heart. The black line on the bottom there shows the relative fluctuation in pressure on the right ventricle, but you see that the red is the pulmonary artery curve for the fluctuation in pressures. It's going to match during systole to what's happening in the right ventricle as the blood is entering into the pulmonary artery. But one thing you will notice is that you don't get as steep a drop after systole is done, okay? Part of the reason for that is because your arterial blood is going to go into what? Where is it going to go? What receives that blood? Hemodynamics. Arteries to arterioles to capillaries. So basically it's getting ready to go into a capillary bed. So it's entering immediately into resistance vessels, and it basically slows it down, and it has a slightly higher pressure as it's going through diastole, looking at that artery curve, because you're trying to take blood that is at a roughly equivalent cardiac output to the left side and slow it down sufficiently so that it will get into the capillaries without damaging them. On the bottom, it's just showing the fluctuation between systole and diastole on the pulmonary arteries. That's your pulsatile blood. We'll get to pulsatile versus non-pulsatile in a little bit. And shows that you have now non-pulsatile circulation happening from the capillaries back on the venous side. These are typically some rough capillary pressures that you're going to see for the pulmonary circulatory system, and it's going to have a big role specifically when we start talking about the capillary dynamics. Now, one thing I want to point out here is the fact that I have an interstitial pressure, which is your hydrostatic pressure, as an outward force. Normally, hydrostatic pressure in the interstitial space would promote movement which direction? Into or out of the capillaries? Into, right? If it's positive. Okay? So normally, if you have a positive hydrostatic pressure in the interstitial fluid, then it's considered an inward force. But this is a negative value. So what you could do is, if you wanted to set up your normal equation, what you actually have here is -8 millimeters of mercury. Okay, so if you were to add these up, 7 plus 14, positive 21. 28 plus a -8 gives you 20. So you still end up with that net filtration pressure that you see down here at the bottom, which is that +1. Okay? The way this is showing it is to say that now that your interstitial pressure, your hydrostatic interstitial pressure, is a negative value, it's actually one of the forces that's contributing to the movement of fluid out. Okay? Now, if we want to move fluid into the interstitial space, one of the things that is very helpful is that because of this negative interstitial pressure, it effectively functions as sort of a vacuum, not a true vacuum, sort of a mechanical suction of fluid, so that any fluid that enters into that interstitial space is either going to be pumped out through the lymphatic system, or any fluid that tends to accumulate in small quantities inside of the alveolus will be basically mechanically sucked back out into the interstitium and then filtered through the lymphatic system or sent back into the capillary bed. So the negative interstitial pressure inside there means that you will have a flow of fluid that will tend to be drawn out of whatever you find inside the alveolus. This is responsible for keeping the alveoli dry. But you don't want to just have normal physiological circumstances that mean you don't have any fluid going into the alveoli. Why do we need fluid inside of the alveoli? Just small coating, like a mist. Why do we need that? What happens if cells die out? Do they live? No. Your epidermis, not living cells, right? They're there to protect all those living cells inside that need that fluid. So you do need to have your cells hydrated, but you don't want enough water in there to actually contribute to coating that alveolar surface and therefore infringe on gas exchange. So if you have too much filtration and too much fluid accumulation in the alveoli that it can't be taken back out, you can get pulmonary edema. Now, pulmonary edema, a couple examples here would be left-sided heart failure or damage to the pulmonary membrane. So if you have damage to the pulmonary membrane, you can tend to get more fluid leaking out into the lungs that normally shouldn't be able to cross through that barrier of the cells. If you have left-sided heart failure, what does that mean? If your left ventricle is not functioning normally, it can't pump out as much. What does that do? It backs up the fluid, okay? If the contractility goes down, so your inotropia on the left ventricle goes down, you have less strength to pump out the fluid. That means that more is going to stay as your end diastolic volume, and there's going to be less room for stuff to come in from the atrium. Less stuff coming in means there's going to be a backup into pulmonary venous circulation, and that will increase the hydrostatic pressure in the pulmonary capillaries. Elevating that hydrostatic pressure in the capillaries can lead to excess amounts of fluid being filtered out and pulmonary edema. The same principle is what we talked about happening with peripheral edema if you had right-sided heart failure. It's the backup of fluid that changes the hydrostatic pressure inside the capillary bed that forces more fluid out than normal. Now, we do have a safety factor for stopping pulmonary edema from happening. And all of it has to be met in order to result in pulmonary edema. So that negative interstitial pressure, hydrostatic pressure, is going to have a big role specifically in being able to make sure that fluid that would enter into the alveoli is mechanically sucked back out. The lymphatic pumping is going to play a really big role in allowing for the movement of fluid that does accumulate in that interstitial space to be pumped out of that general area. And the decreased interstitial osmotic pressure has to do with being able to allow any fluid that does accumulate in there not to stay in there, but to enter into the lymphatic system so that it can actually be pumped out. Okay, so all three of these have to be overcome before you actually get pulmonary edema. Now, pulmonary edema specifically is fluid inside of the alveoli, so inside of your lungs. Fluid in the pleural cavity, so we talked about getting air in the pleural cavity. What was that called? Pneumothorax, right? So pneumothorax is air getting inside that pleural space. If you have fluid, that's called pleural effusion. It's EFF-USION. Pleural effusion can be one of two different kinds. You can get transudative or exudative. All right, hang on a second. Sorry. Okay, you can have transudative or exudative. Transudative basically means that it's what we just talked about. If you have an excess amount of hydrostatic pressure due to left-sided heart failure, what else could cause it besides left-sided heart failure? What else could cause a buildup of hydrostatic pressure backing up into the pulmonary circulation? What else could you have a problem with on the left side of the heart? Oh, you had another argument?
I was going to say enlarged right side of the heart.
Enlarged right side of the heart? Why would you have an enlarged right side of the heart?
I don't know. Probably for different reasons.
No, I'm asking, what are the things that you would have, why would you have an enlarged side of the heart at all? Because you're trying to overcome what? A higher pressure, right? So you can get pulmonary hypertension that your right side of the heart would be hypertrophy to try and generate sufficient amounts to overcome the excess afterload on that side. So you can have pulmonary hypertension, which means higher blood pressure going into the circulation. So yes, that's typically the result of a backup from the other side, and it's the right side responding to the elevated hypertension that you would find because the fluid is not able to get through, so it's getting backed up all the way to the arterial side. So that's a good point. Elevated side on the right side is a consequence of this backup of fluid. What about your valve issues? What happens if your mitral valve is stenosed? So calcified or something that's causing it not to open very well.
Greater pressure.
You're not going to get as much going in. You need a greater pressure in order to get it into the ventricle. You're going to have a lower end diastolic volume, right? If you have a lower end diastolic volume in the ventricle, less of it's leaving the atrium, it's backing up. That same kind of thing can cause excess in hydrostatic pressure inside the pulmonary capillaries, and therefore you can get fluid in the pleural cavity. So left-sided heart failure, mitral valve stenosis, or regurgitation can both cause an elevated amount of what's called transudative pleural effusion. That is specifically the accumulation of fluid that is due to changes in the capillary dynamics without altering the integrity of your vessels. So basically your blood vessels, your lymphatic vessels, they're still intact, they're fine. It's just more fluid is being moved out than there is being removed, okay? Because it's just an increase in overall fluid, it's clear. It's pretty much protein-free, cell debris-free. It's a relatively clear fluid or transudative. Exudative is typically due to inflammation, tumors, any kind of damage to your capillary or lymphatic walls that would allow excess fluid to show up in this intrapleural space. If the problem is inflammation and damage to the vessel walls, what would you expect the appearance of that fluid to look like? Would it be clear? No, it'd be a little more cloudy. It's probably going to have larger molecules like proteins, sometimes even solid material, depending on how severely damaged it is. So lymphatic tumors that could cause a blockage in the lymph system would be an example. Any kind of inflammation that would result in damage to the endothelial cells. Bacterial pneumonia would be an example of something that could cause exudative pleural effusion. So two main reasons to get fluid, two different sets of causes. Okay, and you can tell if it's transudative or exudative based on the color or the turbidity of that fluid. Anybody have any questions about pleural effusion? Yeah.
So if gas is considered a fluid, why do they have a different nomenclature?
Sorry, say again?
So if gas is considered a fluid along with like what we think of as traditional fluids, liquids, water, why is there a difference in nomenclature?
In terms of like partial pressure and
No, between
concentration?
pleural effusion and what we previously talked about in last lecture. So having fluid in the pleural cavity versus having like water or gas in the pleural cavity.
Pleural effusion does have a similar effect in terms of causing compression and decreased gas exchange, but an issue with air coming in will actually push on it and can cause the lungs themselves to collapse. This is going to typically permeate the entire area. It's not going to necessarily, it'll be restricted to a certain part, that's where that damage might be, but the difference in fluid versus air, you're still not getting gas exchange just because it's air that's causing the problem, but the air tends to also increase that pressure because it's not as, I guess, thin, it's a little bit bigger volume typically when it comes in. It's gonna tend to push and collapse that lung. So your alveoli that normally are going to be involved in gas exchange are going to be impaired in both of these circumstances. It's just a question of what's causing that. So they have two different names because they will have two different solutions to whatever the problem is. Any other questions? Okay. That's basically it for that circulation stuff. So now we're going to start talking about hemoglobin. How many people know about your oxygen hemoglobin dissociation curve? Yay! We're going to talk a lot about those today. All right, so heme, that's heme. It's got 4 puryl aromatic rings, not carbons, that are surrounding a ferrous ion. That ferrous ion is critical for being able to allow oxygen to bind. Heme is going to be at the center of your hemoglobin molecule. It's going to be surrounded by 2 alpha and 2 beta subunits of your globin proteins. Okay, so 4 different subunits, all of which are going to be linked to heme, and they are going to be centered on that ferrous molecule, or ferrous ion. So Fe2+ is critical for allowing oxygen to bind. If that turns into Fe3+, so ferric ion, you can't bind oxygen anymore. Okay, so we're going to get to that in a second. The changes that happen to heme when you bind oxygen is a conformational change, specifically in terms of this overall shape. What we have here is that blue is your deoxygenated or non-oxygen bound version. You see it has a little bit more of that, I don't know what the word is, drawing blank. It's kind of got an angled appearance, especially down with the porphyrin rings that are anchored to where the part of the heme section there, those porphyrin rings, there are 4 of them. Remember that are surrounding that Fe2+. That ferrous is where your oxygen is going to bind. When oxygen binds sufficiently to your hemoglobin molecule, this will snap into that red state. That's a more planar state. So the blue is considered T or tensed conformation. R, or your relaxed, is what is shown in red. So when oxygen binds, your hemoglobin shifts to the R state. Now, it's important to note that it doesn't shift when 1 oxygen binds. Sometimes it doesn't shift when 2 oxygens bind. But the cooperative binding that you find of all 4, the reason that you see that cooperative binding is that what happens is you have steric hindrance that prevents, or makes it a little bit more difficult for oxygen to bind when it's in the T state than when it's in the R state. R has like 200 times the affinity for oxygen. Okay, so once hemoglobin is in the R conformation, you can really readily bind hemoglobin. That's why they said before, whenever you guys took this previously, as you bind one oxygen, it makes it easier to bind a second one, which makes it easier to bind a third one. It's not, sorry, it's not really so much that every individual one is going to cause a change. This whole thing happens at once. All 4 of your molecules, all 4 of your subunits have to snap into that R configuration at the same time. You can't have one of your globin's subunits snapping and then another one staying the same. Because of the steric hindrance and the way that they're tightly interacting with each other, that histidine in the middle, that guy right there, that histidine right there, that is critical for the overall function of this interaction. If you lose that or you mutate that, you're going to alter the ability of hemoglobin to function and respond to this conformational change, specifically when oxygen binds. But what you really need to know is that each one of your oxygen binding has an effect on the stability of that T state. So because it sort of is squeezing into a place that it's not terribly comfortable with, it causes it removes a little bit of that steric hindrance that allows for another oxygen to bind. Once sufficient amounts of oxygen bind to a particular hemoglobin molecule, the whole thing will snap into that R conformation. And that's what you see in that red. So it's a more planar, linear appearance here, as opposed to, oops. I don't know why I got rid of my other line. Sorry about that. Okay? Now, you remember when I said that it has to be that 2 plus? You could have a situation where oxidation from ferrous to ferric happens spontaneously, but it could also happen because of different types of jobs. Some sulfonamides can actually cause that change, and what you end up with is methemoglobinemia. So methemoglobin is hemoglobin that has that, that ferric iron attached to that middle side. And what it does is it makes it harder for oxygen to bind. It cannot bind if that's been oxidized. Now you normally have enzymes in your body that are capable of reducing ferric to ferrous. So this will happen spontaneously. But you do have a cytochrome B5 reductase that will it'll use the reduced form of NADH in order to convert ferric to ferrous. That one is, let's see if I can write this as neatly as I can. It's cytochrome B5 reductase. It's also called NADH methemoglobin reductase because it utilizes the reduced NADH in order to convert ferric to ferrous. So your body does have a way to fix methemoglobin if it does form spontaneously or if it forms because of drugs. But there's a very rare condition where you can have a mutation in the gene that's specifically related to this that can cause you to be incapable of changing that. Yeah?
Does it convert ferric to ferrous or from ferrous to ferric?
Ferric to ferrous.
So
3 plus to 2 plus. So from the one you don't want to the one you do want. So you can get spontaneous oxidation of 2 plus to 3 plus, and this enzyme can convert it back.
When you have the oxidation from ferrous to ferric, would you say oxygen is unable to bind? That's more difficult to bind.
It can't.
at all.
It can't bind. And typically you could have about 1.5% of met hemoglobin circulating in your body at any given time just from spontaneous oxidation. It's when it gets up to like 25% that you start to see a big problem in your oxygen carrying capacity of your blood. Okay, so this is a normal process, which is why you have an enzyme that's capable of being able to fix the issue. Now, there are actually two different forms of the enzyme. There's a soluble form and a membrane-bound form. The soluble form is the one that's found in your red blood cells. The membrane-bound form is found in all the rest of your cells except for red blood cells. So depending on the type of mutation, you can have type 1 or type 2 of this particular condition, and it can either affect your blood cells or just affect all of your body specifically. So you don't have to worry about, which type it is, but it is a very rare condition, and it's a mutation in the third isoform of this particular gene. There are 5 isoforms. The third one is the one that causes that.
In individuals with sickle cell, is this mechanism altered?
I'm getting to that in just a little bit. That's actually coming up very soon. Does anybody have any questions about the tensed in blue versus the R, the histidine, the ferrous, or the conformation?
So, when one oxygen binds that it turns into the R state, or is it?
Not necessarily.
Does it gradually become R? Or?
So it doesn't gradually become R. There is one point where basically you can think of it as discomfort. Every time an oxygen binds, as long as it's in the T state, it's kind of unstable. It's binding okay, and it's going to stay put because of the elevated oxygen partial pressure in the blood. And so it sort of forces it to bind, but it creates a little bit of tension. You can think of it as tension in the T state. So the more oxygen binds, the more tension there is, and at some point you get an automatic shift of all 4 subunits at the same time, and they all pop into that R state.
Mm-hmm. So there's no specific point when that happens. Just
It could be after 2 binding, it could be after 3 binding, it just depends on the individual hemoglobin molecule.
Okay.
Yeah, so, but that's why you tend to see that exponential increase in the ability to bind to oxygen. As you increase the partial pressure of oxygen, you see that more of your hemoglobin is going to tend to be in that R state and more readily bind than in the T state, which is what you find at low oxygen temperatures. Any other questions about this before we?
Dr. What was the disease again that was more met hemoglobin?
Oh, it's actually called methemoglobinemia. So methemoglobin in the blood, and there are types 1 and 2. But that's basically just a defect in this. This enzyme is the natural response to oxidation that would happen.
What's getting oxidized and reduced in the redox reaction from that?
Oh, NADH.
So,
NADH.
Which one is, NADH is being oxidized?
It's being oxidized, yes.
So then ferrous to ferric is a reduction.
Ferric to ferrous.
Ferric to ferric.
Yeah, so you're basically ferric plus the NADH is being reduced to ferrous.
So methemoglobin has to be reduced.
Yes, to get to that 2+.
I thought I heard oxidized earlier, so that's what I was.
Yeah, so you get spontaneous oxidation going to ferric, and then it has to be reduced using this enzyme in order to get it back to that reduced state so the oxygen can run. Any other questions before we start going into actual dissociation groups? Okay. All right, so this is from the boron book. I'm not sure if I mentioned it yet, but you will notice that a lot of these figures for respiratory are going to come from the boron book. I would recommend going through that one for respiratory. I had recommended Guyton and Hall specifically for a lot of the ECG stuff when we did cardiovascular. It's a little bit better for the clinical relevance. But for the stuff that we're going to cover in respiratory, boron is going to be a better book. Now, this is really showing you how you create your oxygen dissociation curve. It's done experimentally because what you really want to do is not just know how much oxygen is bound to hemoglobin, but you need to know how much oxygen total is in the blood. So you would pick whatever PO2 you want to have, so whatever partial pressure of oxygen, and you allow it to equilibrate with whole blood. There's going to be some of that oxygen that will be dissolved in the plasma. There will be some oxygen that is dissolved in the water inside of your erythrocyte, and then there will be a large portion of it that's actually going to be bound to the red blood cells. basically what you do is after you incubate it for a while at various partial pressures, so you'll do it at various ones, and you will assess by centrifuging this down. You'll look at the oxygen content that's dissolved and the oxygen content that's in the red blood cells, taking into account the small portion that is probably dissolved in the cellular water inside of those red blood cells. So by taking those two pieces of information at all of these different partial pressures of oxygen, you can plot them on a graph to see exactly how much oxygen you're finding inside of whole blood and inside each of those two parameters over the course of various tension or partial pressures. So that's where you get this value. That brown curve is your hemoglobin oxygen dissociation curve. That is what you typically see. If you were to look specifically at the dissolved portion, you see that it's relatively low. That's down here at the bottom. It stays pretty small, but that small amount contributes a little bit to this difference up at the top. Okay? So at point A, that's showing your arterial blood, and V with a line over it is your mixed venous blood. Has anybody worked in an office where you talk about mixed venous versus central venous blood samples? Okay, so mixed venous is typically what we are going to talk about, and it's basically all the blood that goes into the pulmonary artery. It's mixed because it's coming from your coronary veins, it's coming from your superior vena cava, which is head and upper extremities, and your inferior vena cava, which is, gut, viscera, and lower extremities. Pulmonary artery catheters, from what I understand, are not really used all that much anymore. It's a little easier to sample from the jugular subclavian veins, and that will actually give you a central venous value. That's your central venous blood, because it really only samples from your head and your upper extremities. They're not always identical, but they're typically used sort of in conjunction with each other. The purpose of using mixed venous is because if you just sensed from or sampled from any systemic vein, you're really only going to get blood gas information coming from certain parts of the body. If you get it from the pulmonary artery, then you get an idea of how oxygen is being utilized by your entire body. Because it might be different on your upper extremities versus your lower extremities versus your heart. Okay? So even though central venous samples are easier and more frequently used now, the pulmonary artery gives you the best overall view, and so when we talk about that V with a line, that's what we're talking about. We're looking at, if you were to take a sample in the pulmonary artery, all of the blood coming from your systemic circulation, mixed together, what's the oxygen content there? Okay, and you can see that that value is going to have not only a lower hemoglobin saturation, but it's also going to have a lower oxygen content. So you have two y-axes here. The saturation is what we see on the left. The actual content of milliliters of oxygen per deciliter of blood is shown on the right. That little red curve that you see, that is your hemoglobin bound. Most of your blood or oxygen level is coming from hemoglobin bound. The only reason you start to see these two lines kind of diverge from each other at this point has to do with the point at which you finally start to see the dissolved coming up more above baseline. As it starts to come up above baseline, then you start to see a difference in the amount that you can put attributed to hemoglobin versus the total oxygen content of that whole blood. Okay, so you can sample oxygen content, then centrifuge, and look at what's in the plasma, so what's dissolved, and then what is actually bound in hemoglobin. When we talk about the dissociation curves, because they're so similar, you can measure total and just have a rough subtraction of the amount that's actually from the dissolved portion to get the full oxygen hemoglobin saturation. All right, now, this one I think I made available ahead of time, just specifically so that we could look at the two different types of content. For the arterial value, on the right-hand side, in milliliters of oxygen per deciliter of blood, we have a value of 20. That's your oxygen content in arterial blood. So arterial systemic arterial blood. Okay, so if I'm going to talk about pulmonary arterial blood, I will say pulmonary artery blood, okay? Your mixed venous blood is going to come from your pulmonary artery. It could come from your heart, but it's going to typically come because it's easier to catheterize the artery itself. Your O2 content of your mixed venous is what you would see from this line here. So we're looking at this one, for down here, and this one up here. Oops. Sorry about that. Really sorry. The difference between the two of them is about 4.7. So the difference between the oxygen content on your arterial side versus your venous side is about 4.7 mils of oxygen per deciliter of blood. What does that mean? Why the discrepancy?
You can see the exchange of oxygen.
You can see how much is actually being used, right? See how much is used by your tissues. How much is there when it's considered oxygenated and going into your circulatory system, and then how much is left after you've had gas exchange at your peripheral tissues. Okay, so that difference for that total oxygen content gives you the amount that was used. Okay, so here's our dissociation curve. And we're going to look specifically at these different values. Normal arterial blood concentration, and blue for our deoxygenated mixed venous. It's going to hover around 100 or so for arterial. It's going to hover around 40 for mixed venous. This one is actually from the Guyton's book, I believe. It's looking at the volumes percent that you have of oxygen, so that's your content of oxygen that's present inside the blood. If you are exercising, what do you notice about the oxygen content in your venous blood? It's lower, right? It's on the lower end of this oxygen hemoglobin dissociation curve. Why is that? You're using more, right? You're using more. If you're exercising, you need more energy. Your tissues, your cells are going to use a lot more of that oxygen as it passes through systemic circulation, so you're going to end up with a lower content. So the value that we had for the oxygen content of 4.7 is going to be bigger, okay? Now, your cardiac output will also increase to try and accommodate for that, to speed up the amount of oxygen delivery. The point I want to point out here specifically looks at, we already talked about the oxygenated blood leaving the lungs, the reduced blood that's returning. So toward the right end of your dissociation curve. That is what's found at higher partial pressures of oxygen. So if you have a higher partial pressure, down here at the bottom, a higher partial pressure of oxygen, which is up around 190 to 110 in that general area over here, this is what you would find in the lungs, so you're pretty much completely saturated. When you get to the tissues, this is roughly the concentration or the partial pressure of oxygen that you're going to find in the tissues. So your hemoglobin is going to become less saturated, which means that you're going to have less oxygen actually bound to the hemoglobin. This is going to turn out to be a very good thing because you want oxygen to be released so that carbon dioxide can bind to the necessary binding spots and allow for it to be removed from metabolically active tissues. All right, so our pulse oximeter. I'm sure you guys know what that is. You've seen that before. You're putting it on your finger, your toe, depending on, how old you are. Kids, they usually have to put it on their feet. But what it's really doing is it's looking at the oxygen content of pulsatile versus non-pulsatile. Why do we care about that? What's pulsatile blood? Where the circulation is at? Arterial, right? What about non-pulsatile? Venous. Okay? So basically what your pulse oximeter does is it shines red and infrared light through like a nail bed through the skin, and it reads it on the other side. And it's measuring the absorbances. it turns out that oxygenated hemoglobin is going to absorb red and infrared light at a different value than your deoxygenated hemoglobin. So you can look at the pulsatile and the non-pulsatile components in order to figure out what that difference is. If you take the total amount and subtract the non-pulsatile value, you can get whatever the oxygenation was on the arterial side.
Is the infrared absorption due to the histidine residue?
That's a good question. I'm actually not sure. Anybody know? Yes, if the infrared absorption has to do with the histidine, the imidazole ring on the histidine residue.
This absorption normally happens because of like cyclic compounds.
Right, aromatic compounds, yeah. So I would imagine that has a role, but you also have those porphyrin rings. You have 4 of them that are present in the heme, not just the.
Do the porphyrin have aromatic? Okay.
Yeah, the aromatic carbons. There are 4 aromatic rings around that iron, and then you also have that aromatic histidine. So I'm not sure what's actually triggering the difference, but I'm sure that it probably has a role. Yeah. Okay, so the saturation is calculated specifically looking at the total amount of absorbance minus your non-pulsatile absorbance, right? Because you look at the total amount, get rid of the amount that's from your venous side, and you can figure out what the pulsatile or arterial saturation is. Why can't a traditional pulse oximeter, there are carbon monoxide pulse oximeters, I know this, and we don't have to worry about that, you have a way to be able to test it, but traditional ones can't detect carbon monoxide poisoning. Why? Because it looks similar, because carbon monoxide binds to hemoglobin. And because it binds to hemoglobin, it will have a similar absorbance to oxygen-bound hemoglobin. So you won't really be able to tell the difference. We are going to talk extensively about carbon monoxide in just a little bit. But the pulse oximeter is really taking advantage of looking at your oxygenated and deoxygenated based on the fact that they respond differently and they absorb differently at different wavelengths, those red and infrared lights. Okay, coming up on a couple of questions. So, oxygen transportation in the blood. Starting off with your basic hemoglobin value, about every hemoglobin molecule can carry 1.34 mils of oxygen per gram of hemoglobin as a total amount. You collect all of your hemoglobin molecules, make up 1 gram, you get about a little less than 1.5 mils of oxygen. Under normal circumstances, for every deciliter of blood, you have 15 grams of hemoglobin. Okay, that would be considered normal. If you're anemic, that could be down to like 10. So the normal oxygen carrying capacity would be about 20 mils per deciliter. For somebody who's anemic, it's about 13 would be an example. These values can be used to set up calculations based on how much of that hemoglobin is saturated. And you can calculate the amount of oxygen that is being transported in the blood. So the first question I want you guys to take a second and see if you can work out is looking at how much hemoglobin is saturated under that particular level of hemoglobin and your oxygen content being that value. Don't worry about units, just put in the number that you have. lot of people are getting, a more exact one that I put in here, because I wasn't assuming that everybody was gonna have calculators, so. The actual answer is that 48.5. So, let's take a quick look at my hopefully relatively neat handwriting. Okay. So, we were specifically looking at, the percent saturation of hemoglobin if they had 10 grams per deciliter of blood and a venous oxygen content of 6.5 mils of oxygen per deciliter of blood. So the first thing that you want to do is say how much hemoglobin do they have and how much oxygen can be carried per gram of hemoglobin. So they have 10 grams of hemoglobin per deciliter of blood, and the oxygen carrying capacity of hemoglobin each gram is about 1.34 mils. So together, you get 13.4 mils of oxygen per deciliter of blood in this person. This is their maximum oxygen carrying capacity. They can't carry more than that. They have a value of 6.5 in their venous oxygen content. So what is the percent saturation in that blood? It's just 6.5 divided by whatever their maximum oxygen content is. So the percent saturation here is a little bit less than 50%. You guys see how we got that? Okay. All right, next question. Oh, it didn't go to my next question. Come on, go back. Okay, there we go. That's what I wanted to do. All right, so now take a second and say, if I give you an oxygen saturation, so hemoglobin saturation is 60%, and this person has a level of 15 grams per deciliter, how would you get the actual oxygen content? So it's sort of a reverse of what we did just now. Okay. About another minute. Or 30 seconds. We still have more content. Stop you. Not showing me anything. So 12.06, I put 12. So 12.06 is also correct, which, so more than 16, got it right. We had a lot more people. But quickly running through that, for those of you that maybe didn't pick up on that right away. Looking at our question, we had 60% saturation and a hemoglobin level of 15. So again, you have to figure out whatever the maximum oxygen carrying capacity is. And in this case, we're looking at 20.1. What's 60% of that? It's about 12. Okay? So you can figure out the oxygen carrying capacity that is maximum, and you can figure out what the amount would be of the venous or the arterial blood based on the percent that is actually saturated. Does anybody have any questions about these? All right, so what about under anemic conditions? If hemoglobin is going to carry the vast amount of your oxygen, what happens if you don't have a lot of red blood cells? Let's say you have hemolytic anemia.
I don't know the answer. Is this a new lecture? Is it?
It shouldn't be. Does it not show up?
Oh, I thought that you had like an O2, CO2 heading. So this is still continuing with the previous lecture.
It should be.
Okay, sorry.
No, it's fine. If we're having issues getting this to switch from questions to outside questions, I can just restart the presentation and have it really mess me up. Okay, this is not cool. All right, so the vast majority of our oxygen is going to be carried by hemoglobin. If you don't have adequate levels of hemoglobin, you're going to reduce the amount of oxygen that's being able to be carried in the blood. So back from our oxygen dissociation curve, remember the brown curve is everything all together. It pretty much lines right up with the red curve. You only start to see a little bit of a difference at very high partial pressures of oxygen when you see more of that oxygen showing up in the partial pressure in the dissolved portion of your blood. So, how's the body going to compensate for a decrease in hemoglobin levels? What do you think you would do?
Make more red blood.
You can make more red blood cells, but if there's a problem with them constantly getting destroyed, it's going to be a constant battle, trying to produce enough to compensate for the amount that's being destroyed. What else could you do in order to try and compensate for a lack of oxygen carrying capacity per unit of blood? Increase the rate at which blood is being delivered to the tissue. So if you increase your cardiac output, you can increase the rate at which oxygen is getting delivered and carbon dioxide is getting carried away. Okay, so the obvious fix is get more red blood cells, right? But it does take time to produce red blood cells and get them out into circulation and allow them to mature. So you have a couple of different things. Both of them are going to happen at the same time to try and maintain adequate oxygen delivery to your tissues. This comes into our sickle cell problem. So, normal hemoglobin, which is on the top, that hemoglobin A, that is typically what you're going to see for the amino acid sequence. This valine, which is the substitution of that glutamate. If you get that glutamate, that glutamate to valine solution, which I want to erase that so you can still read it. That is due to a single nucleotide polymorphism. So a SNP. Anybody who's done any kind of research or taken any classes talking about SNPs, it is one base in the sequence that causes a shift in the amino acid encodes. So you have a missense mutation that results in a glutamate turning into a valine. That has a huge impact on the ability of the hemoglobin to stay soluble under conditions of low temperature and low oxygen tension, okay? It makes it so that under conditions of low oxygen partial pressure, so under exercise, under lower temperature conditions, what actually happens is you end up getting this crystallized form. It becomes less soluble under low PO2. So you can get sickle crisis that happens under certain conditions. It can be reversed if you give them oxygen to bring their PO2 up, or if you warm them up. If you get them out of that sickle crisis, they can return to normal. It is only something that happens under particular conditions. But the result is that because of that valine now located where glutamate should be, it disrupts the normal folding pattern and interactions of the subunits of those alpha and beta globin chains. Now, this is talking about the beta globin chain. It's a glutamate to valine substitution in the beta globin. If that mutation occurs, then you get this crystallization forming under certain conditions and it gets these sickle type appearances. What happens if you have a lot of these sickle red blood cells floating around circulation? You can get occlusions, right? Because these are not nice and round like inner tubes. Instead, they have edges now. And those edges can link to each other. They can get caught on integrins and adherins on the sides of your cell walls, cell membranes, and it can cause blockages in some of your vessels. Now, which vessels do you think are most likely to be affected? Capillaries, right? They're very, very thin, very small diameter. And because of that, any kind of clumping that you have is more likely to cause an occlusion. And if you have an occlusion, what does that mean for oxygen delivery downstream of that occlusion? Non-existent, okay? So not only do you reduce the oxygen carrying capacity because of the sickle mutation, you can also cause disruptions in overall blood flow to certain parts of the body as a result of being in sickle crisis. Now, like I said, this is something that's reversible. So by giving somebody oxygen, you can actually help to bring them out of the sickle crisis, warming them up. There are a number of different things. If you also were to get rid of some, so you can get this under respiratory acidosis as well, under exercise conditions, but it's a reversible trait. The problem is that if you are homozygous recessive for sickle cell trait or sickle cell anemia, then you will have this occur. People who are heterozygous typically have a moderate reaction, but really nothing that causes any kind of symptomatic response. And it can actually be protected in certain areas, like malaria endemic areas, because they specifically live inside of your erythrocytes, and sickle hemoglobin is not something the parasite is happy with. Any questions about sickle cell?
This is a weird question. Like, I've seen people who say that like they're like in pain, that could come from like the occlusions and like stuff not being
Yep.
done. Okay.
Yeah, it's the occlusive nature and the lack of blood flow, that ischemia that results downstream of those occlusions. It causes physical pain in sickle cell patients.
Okay.
Any other questions? Who knows this guy? Who knows why I have a picture of him?
Blood.
Yes, blood doping. Not good for integrity among sports, but very helpful in actually improving your athletic performance. Why? What is blood doping? So you can do it two different ways. You can either increase your erythropoietin, like by using a synthetic recombinant erythropoietin, which helps to promote more red blood cells to be synthesized and also can tend to have a moderate increase in the amount of hemoglobin that's produced inside the body. You can also just put red blood cells in the body. What does that do to your oxygen carrying capacity? It increases it, because now you have more grams of hemoglobin per deciliter of blood. What would be a problem if you did this too much?
Blood pressure raises.
Blood pressure raises because what raises?
Viscosity.
Viscosity, right? If you're elevating your hematocrit by elevating the amount of red blood cells, you're going to increase the viscosity. And you remember from R equals 8 eta L over pi r to the fourth, viscosity in the numerator, more viscosity, more resistance, higher blood pressure, okay? So you can end up with polycythemia if you are not careful and do blood doping in excess, okay?
Didn't
Yeah.
they say the normal hematocrit was around 46 to 48%?
So yeah, it varies because it's also different between men and women.
Okay.
So typically we just sort of say, let's say around 0.4 just to make it easier to calculate. But yes, it usually hovers between 40 and 50%. But not usually above 50%. Anything above that would typically be
And
above.
does the blood doping take that, I assume, above that typical 50%?
Mhm.
Okay.
Yeah, because if you are either adding red blood cells, then you're physically adding cells to increase that. But if you are using erythropoietin, your body's producing more red blood cells. And they typically last about 120 days, which would be different from like the 12 to 20 days that a sickle red blood cell would survive. So if you're increasing the production and they're still gonna have that same lifespan, they're gonna die off at the regular rate, but you're producing a lot more. So your overall hematocrit's gonna go up.
So how do you test if somebody's doing this?
How would you test?
Yeah.
So typically what people are gonna do is use erythropoietin. So you can test for erythropoietin levels.
Wouldn't the roof recording levels increase if you lived in high altitude, low
Uh-huh.
oxygen
Yep.
situation? So how about those people who live there all the time? They're mimicking blood doping, so do they have problems?
So, no, that's actually a natural way of doing it. If they find that, so you can measure the difference between endogenous and synthetic because they have different, signatures in the way that they're produced. But, we're actually gonna talk about that in lecture 15, we do high altitude physiology, because one of the things that you can do to naturally increase your oxygen carrying capacity is just train at high altitudes. So a lot of runners would tend to go to someplace more elevated, go up to Denver to go running, or if you want to, go over to, Cusco and go running. That, would be an adventure in and of itself. But if you are at a higher altitude, your body is going to adapt because your oxygen partial pressure is a lot lower. And so you're gonna have to increase the ability to bring that. And if you reside there, we'll talk specifically about some of the changes that you have to adapt over long term, but you can make short-term adaptations as well. Good question. Any other questions about that? Okay. Now we're gonna get into changes in our oxygen dissociation curve. So, what is most likely to shift your hemoglobin into a tensed state? So remember what your tense state does, and which one of these would be most likely to shift it. All right, I see a lot of correct answers, so I'm only gonna give you another 5 seconds. I think you got this pretty well. All right, so, which one? Low pH, yes. Low pH is going to shift it to that tense state. That tense state means what? Oxygen wants to bind or doesn't really want to bind as much? Not as much, okay? The R state is the one that has about 200-fold higher affinity than you would normally found. Fine. So, in metabolically active tissues, you have an increase in your chances of oxygen unloading. So, high demand for oxygen, which means they're producing a ton of carbon dioxide. If you have high carbon dioxide, what happens to your pH? Down, right? So that methyl red experiment that we saw with the soda water versus the regular water, right? That's exactly what's happening here. If you have a lot of CO2, you are shifting that curve, you're producing a lot of protons, and that's making that more acidic. Your tissues are also going to be warm. Why? You're generating heat, and what else are you doing? Because you are increasing your metabolic demand. How are you going to get oxygen to it? You're going to increase blood flow, right? So you're going to increase blood flow, your blood flow is warm too. So your tissues are producing heat just from metabolism. You're also sending more blood over to those tissues that are metabolically active. So the tissues are warm, they're acidic, there's a high PCO2. All of these are typically found in metabolically active tissues. And what happens is that causes a shift in your overall oxygen dissociation curve. So, what we're looking at here is the red is showing your normal kind of steady state value if you have a high temperature. So, this is considered comparatively a high temperature. All right, and then this would be your comparatively low temperature. Which direction do you see it shifting when your temperature goes up? To the right or left? To the right. What does that mean? At your tissues, you typically have a value of about, it's not letting me write, about 40. Partial pressure of oxygen, about 40 in your tissues. That means that if you have a higher temperature, at that blue curve, how much of your oxygen is saturated? 64, 65%. What about if your tissue was cooler? Much higher, right? You're looking at above 80s, 85% saturation. So the warmer your tissue is, the less likely your hemoglobin is going to be saturated at that point. Which means the more likely it's going to unload its oxygen to that tissue. It has a lower affinity for oxygen when the tissue is warmer. So when we talk about shifting the curve to the right or the left, it's specifically talking about the hemoglobin's affinity for oxygen. You shift it to the right, it has a lower affinity for oxygen at a given partial pressure of oxygen. If you shift it to the left, at a given partial pressure of oxygen, it has a stronger affinity. Okay? So warming up the tissues means less of it is going to be saturated with hemoglobin at that same partial pressure. All right. What about for carbon dioxide? Which way is it shifting? High blood CO2 is shifting it which direction? From normal?
To the right.
To the right. Why? Metabolically active tissue is going to produce a lot of CO2. That's going to shift this curve to the right, meaning that at any given partial pressure, on this one it's showing a partial pressure of 30, you're going to have less saturation than you would under low CO2 values. Okay, this is going to be a benefit. You want to be able to unload a lot of excess amounts of oxygen at tissues that are producing a lot of CO2 because they need that oxygen to continue respiring, and that CO2 needs to be taken away. All right. So this, well, these two are kind of related. This one is part of the Bohr effect. The Bohr effect specifically looks at the relationship between CO2 levels and acid. Most of the effects of the Bohr effect are going to be due to pH. And the benefits that I wanted to show this one from the boron book is specifically because it shows you what is actually happening here. So up here at the top, you can see that when you have excess amounts of acid, it actually will interact with hemoglobin. Hemoglobin is actually a very good buffer of acid. So if you have acidic fluids, acidic tissues, that excess acid can bind and interact with your hemoglobin. When it does, though, it changes the conformation a little bit and causes hemoglobin to release oxygen. So where in the body do you tend to find more acidic pH? Metabolically active tissues, right? They're producing a lot of excess acid because all metabolism inside of your cells, we don't produce bases from metabolism. We produce organic acids. Okay, so you have acid production just from metabolism. You have acid that is going to be due to elevated amounts of CO2 that shifts that curve or shifts that equation all the way over to the production of protons and bicarb. The protons are a stronger acid than bicarb is a base, so it makes it more acidic. That will interact and be buffered by hemoglobin. This is the major cause of that Bohr effect. You can have an elevation in CO2 without having a change in pH. It is possible to have that if you're able to buffer out those acids with other bases that are present in the body. So that CO2 is pretty much a more minor effect of the Bohr change. But the reason I said it has a bigger effect is you see that this is looking specifically at the PCO2 is staying the same, but your acid is what's changing. So your pH is changing here, but your PCO2 is staying the same. And you see that you have a pretty significant shift to the right when you drop that pH to a lower value. Okay, and that's because of the buffering capacity of your hemoglobin. When we look at carbon dioxide, we see the same basic effects. In this case, we're looking at a constant pH, and we're looking at changes in your PCO2. When that PCO2 goes up here, you see a smaller shift of that curve to the right. Both of them are going to cause that shift, okay? But you're going to see the impact of the pH alone, even if there's no change in carbon dioxide partial pressure, has a bigger impact on the affinity of oxygen to bind to hemoglobin because of the way that it interacts with the hemoglobin molecule. Hemoglobin is a great buffer of protons. Carbon dioxide also will interact with your hemoglobin up here. Oops. It forms what's called a carbamino compound. Hemoglobin does a better job of binding carbon dioxide than your plasma proteins would, so you tend to find more carbamino compounds showing up inside of your red blood cells than you do inside of the plasma. But it has the same basic effect. When carbon dioxide will interact with hemoglobin, it basically kicks out that oxygen. Okay? So the more carbon dioxide you have, the more likely it is to interact with the hemoglobin, and the more likely you will get oxygen release into the tissues from that hemoglobin bound form.
You said that heat also produces a similar effect. So what's the magnitude of that, like in relation to carbon dioxide and heat?
It's more akin to what you'd find in the acid than the CO2, but not as strong as the acid. But they're all shifting it to the right. All right, who knows what 2,3-DPG is? Anybody in biochemistry? You might have heard it as 2,3-BPG. Bisphosphoglycerate, yes. So 2,3-bisphosphoglycerate or 2,3-diphosphoglycerate, depending on what text you read, okay, is an intermediate from what metabolic process? Glycolysis, okay? So if it's an intermediate from glycolysis, what does that mean for your tissue? If you elevate that amount. Lots more metabolism. And is glycolysis aerobic or anaerobic?
Aerobic.
Well,
Anaerobic.
it's anaerobic that can produce what's going to lead into aerobic. But technically, if you don't have enough oxygen to make it into the oxidative phosphorylation, you're going to rev up glycolysis to try and produce more ATP. So if you have an elevated level of production of 2,3-DPG or 2,3-BPG, that means that you have an elevated level of glycolysis, which means your tissues are very metabolically active. So what does that mean? It is shifting to the right because you have a higher level. What that does is it actually interacts in between the two beta subunits. It interferes with the two beta subunits. It binds to that little sort of crevice in between those two subunits. And what it does is, because of the change that it has in the conformation by inserting itself into that position, it causes all four of your oxygens to be unleashed at the same time. As opposed to the buffering effect that you see with protons and carbon dioxide. With this one 1-DPG is enough to pull off all of the oxygen. So any increase in glycolysis in your cells is going to do a really good job of being able to shift this curve to the right to unload more oxygen at that particular partial pressure. All right, one last question before we go. This figure is showing you stripped hemoglobin, which means there's nothing bound to it at all. And then you have it compared to hemoglobin that has bound carbon dioxide, hemoglobin that's bound DPG, that has bound both of these, and whole blood. What do you expect would be more similar to what you would see in fetal hemoglobin? And we only have about a minute left, so I'm not going to let you answer this very long. All right, I'm going to stop you just because we're running low on time. The correct answer is actually the orange one. The reason it wouldn't be the blue is because that's showing that complete state where you don't have anything bound. Your fetal hemoglobin is going to show more like an orange curve because there isn't really a difference in stripped HbF or HbA, but the difference is that 2,3-DPG binds less avidly with our hemoglobin than it does with fetal hemoglobin. Binds less avidly with the fetal hemoglobin than it does with ours, because it binds to that beta chain in ours. It doesn't bind as well in between the gamma chains that you find in fetal hemoglobin. So we're more likely to deliver our oxygen to the fetus because we can bind one of those metabolically active byproducts faster than the hemoglobin field. value. All right, it's 11:31, so I apologize for going 1 minute over. Just wanted to finish that last bit before we get into the way it's transported in